Okay. Good morning, good evening, good afternoon, everyone. Let's get started. My name is Kannan Muthukkaruppan. I'm one of the co-founders at Yugabyte, and here we have on another episode of the YugabyteDB Friday Tech Talk, Piyush Jain, in uh, an experienced engineer in the database team. And I'd love to hand it over to Piyush to introduce to introduce himself and the topic for today's talk, and we can jump right in.
Thanks, Kannan. Welcome, everyone. I'm Piyush. Yeah, I work in the LRT team, that's Languages and Relational Technologies. And today we'll dive into job queues on YugabyteDB and how we can leverage distribution for building good queues. There's a good amount of content we have. It's a bit dense, so let's dive in. Yeah. The goal we have today is we want to build a job queue, and the job queue looks something like this. So you have a bunch of tasks, and you have some workers, and the aim is we want to execute each task once, and we want to leverage multiple workers to work on tasks in parallel, right? That's one thing we want. Plus, we want to minimize contention when we try to synchronize workers across tasks, right? So there should be less waiting from synchronization, so less overhead in sort of picking tasks from the queue, right? And we see this sort of thing time and again in a lot of systems that we build. So we'll try to do this on YugabyteDB today. I'll also just pause me if there's questions, right? Um, so why would you use a database to implement a job queue, right? So I mean, the simple answer is that sometimes you don't want to use really complex pieces of software uh, to create a job queue. Like if you're already running YugabyteDB or some database, you might as well create job queues on them, right? You don't want to maintain extra operations and stuff for job queues. Plus, on YugabyteDB, you already have fault tolerance, scale, persistence, strong consistency, etc. So you can get good guarantees. I mean, the right guarantees by running on like YugabyteDB, right? So
Yeah,
let's
I mean, in some sense, um, there might be some scenarios where queuing is your dominant use case, and maybe it's like you need a message bus to connect different microservices, and there might be valid use cases where you need to invest in a dedicated message-oriented data infrastructure, something like Kafka. But
Mm,
often, if you've already made a selection for a database for your operational use cases, transactional use cases, and you find that you also have a need for a messaging service or a queuing service, why not as well handle it in the database itself? So, and this is not only true for Yugabyte. People often use Postgres or Oracle to just handle their job queue right in the database.
yeah.
Keep
Uh,
going. Yeah.
yeah. So, if we try to create a job queue, the simple version is, let's assume I have a table, and I have ID as the primary key, which sort of represents the job or the task. And there's some payload for the task. And the idea here is that workers can pick tasks in at random, right? It doesn't have to be FIFO order or something. So you insert tasks in some order, but workers are free to pick tasks in any order, right? And sort of remove them from the table. Now, a simple way to sort of pick tasks would be that you like select a task from the table, and you explicitly lock it with the for update lock which Postgres provides, right? And so does Yugabyte. So you lock the task so that nobody else picks it, You execute your task and then you delete the task. And you do this in an atomic transaction block, so that there is isolation, right? Yeah, and no
I
two
think I think you mentioned it, but just to make a point, like in this particular case, you're starting with an example where you're not trying to do a first in, first out order. You're like, I'm okay with any task type of
Yep.
requirement. Okay, keep going.
Yeah. And I mean, the job IDs are ordered in ascending order by the UUID, but those are random. So there's no FIFO ordering in the data layout as well, right? Uh,
Correct.
and I mean, if we quickly try to execute this, right, to see how it performs, let me. So I mean, I have this sort of. Let me open this. The simple case. So we are creating this table, inserting a bunch of tasks, and we try to execute this DQ function, which basically scans the job queue, logs the task, and removes it from the queue. Right? If I just load this, so I have a cluster running, and I created the job queue and the DQ function, and I have this. I mean, I'll keep using this alias throughout the demos, right? In the stock, but I'm using PG bench to run a set of 10 workers with 10 connections, one for each, and they'll keep dequeuing from the queue, right? So if I just run this, we see about
So, Piyush, just one feedback, maybe it doesn't matter. Of
mhm.
your terminal window, the left few characters are getting cut off. Like,
How is it?
uh, but maybe not. I can see the progress. So no, maybe I take it back. Yeah, I can see the word progress on each of the lines.
Mhm.
Yeah,
Okay. Yeah, I mean, we see some throughput around 170, 130. It also keeps dropping. I'll get to that later. But this is what we get if we have a simple queue. Plus, you see some failures. Now, the failures, like two failures here and one, that's because of contention. So sometimes the transactions are blocked on each other and they face conflict errors, right? They're not able to make progress. So that's the simple queue. What would be better, right? So uh, like in this queue, while one worker picks a task and executes it, nobody else can pick a task, right? They are all sort of blocked on this worker. They try to wait in anticipation that worker one, which got this task, is going to sort of fail and give up the task back in the queue, and I'll pick it up, right? But yeah, that does not happen in the common case. So this is a pretty simple model, doesn't work well. Now you can use skip logged. This is something that is already there in Postgres and YugabyteDB. And what happens here is workers try to scan the task. They try to pick a lock. If it's already logged by some other worker, you skip it and you move on to the next one, right? So that's how this works. You have a limit one, so it keeps scanning until it finds a task which is not yet logged. So, in other words, a task which is not yet being processed by any other worker, right? So you don't block on others while they're executing tasks. Yeah. So I'll quickly show this. And this is standard practice, to use skip logged if you're sort of creating a job queue to not block uh, other workers. So if you see, we have much better throughput. More tasks per second are being picked. You don't see failures as well because now you don't have to contend on a single job. You keep moving on in the queue to find the next task which is available. So that's skip logged. Let's let's try to do something better. So one issue with skip logged is so all the workers, they start scanning the table uh, at the start of the table, right? And they keep scanning the same set of tasks. So you'll have to skip a few tasks until you find one which is not being actively executed, right? You can bypass this sort of skipping the same tasks across workers by having workers start at different places in the job queue, right? And you can sort of achieve this by sharding your uh, you know uh, task queue, and so there's one thing. You also need to shard your queue because it helps to spread load, right? You don't have all workers coming to a single node trying to scan and acquire tasks. So you can spread load. Plus, there's so your workers now can go to different shards, but you can also have workers start at different random points in the shard to sort of even lower the contention further. So for example, here I have this table, right? The same table I'm
Yeah,
going
maybe
to
just
start.
to say a few points, like I think there are a couple of things at play here, right? One is if you have two, three workers, maybe it's not as much of an issue, but if you have, say, 100 workers,
Mhm.
and every time a worker frees up, the other 99, let's say, just happen to be busy, they have still 99 logged rows. You don't want to skip past those 99 rows to get to your row. So that is one inefficiency aspect. The second, maybe you're covering later, is as these workers are deleting their respective jobs, deletes in most databases are deferred because of multi-version concurrency control and so on. It's not just a Yugabyte thing. In Postgres and other places, delete tombstones will be left around, right? And everybody's also starting and scanning over those delete tombstones. So that is the second aspect. I think you're covering that. The
Yeah.
third is, of course, leveraging the power of a distributed database, right? Rather than everybody dequeuing from one hotspot, the fact that there could be multiple shards that can be serviced from different servers in a distributed database, by giving flexibility on where you start to dequeue from and randomizing that, you also minimize the hotspot on the same set of servers.
Yep.
Yeah.
Yep. Yeah, and that's well said, well summarized. So I have split like the table at a few points, and what I'm going to do now is have the workers go at a random point in each shard, and try to pick a job from there. So now there's less contention, right? And let's try this. So actually, also let me open the. I mean, we had the sequel on the slides, but what I'm trying to do here is I create a view, and basically we try to pick a random UUID and start our search from there, right? Start looking at IDs which are greater than that. I also do a union all to look at IDs which are lesser, just in case we don't find anything uh, greater than that random UUID, right? We want to cover all jobs. And our DQ function is similar. It's just that we now pick a task, I mean, select a task from the view, and we have the for update skip logged. Right? So,
Basically, it still has the full search space of the table, but you're
yeah.
starting at a random point, looking in one direction, and
Mhm.
you'll mostly find it. If you don't, you still cover it with a union all clause, right, to cover in the backward direction. So
Yep.
there's no correctness issue.
Yeah.
But you'll early exit because of the limit one that you have as soon as
Yeah.
you find a job. Yeah.
That's right. And we have the queue, etc. created. And if I remember, it was about 400 or so, right? Earlier in the previous case
Correct.
without the sharding. Now we have much better throughput, right? We have some 600 and something. Again, this is just 10 workers basic
Correct.
setup.
And the more the workers you have, this randomization gives better win, right?
Yep, yep,
Because otherwise you're skipping past many locked entries. Yeah.
that's right. Um, Yeah, but now like in the so all of this that we are doing, this is not a FIFO queue. We are randomly picking task, right? And they can be inserted in sort of they are not laid out in the order of the timestamp in which they were inserted, right? So let's try to do a FIFO queue, and in a FIFO queue, we still want to keep the queue sharded. So one other reason for that is, if you don't have a sharded FIFO queue, you'll keep inserting at the same sort of head, right, or tail in the database. So you'll have one node which has the timestamps which are close to the current time, and you'll keep hitting that database, right? I mean that node. So you still want to shard your queue to spread the load of insertion. Now,
And in some cases, uh, there might be a natural sharding key. Maybe there is already different queues, like for different logical maybe tenants in your system. Like maybe like a tenant ID might already be a good way to shard it. But if there wasn't a natural one, I think your approach covers the case where logically it's a single queue, and but you still want to sort of bucketize it to avoid hotspots, but still as close to possible give a first in first out semantics.
yeah, yeah, that's right.
Yeah.
Yeah. So
Okay.
here I have a bucket, but I mean you could have something which already acts as a bucket. So, yep. And I just have four buckets here for this example, and within a bucket, the tasks would be ordered by the creation timestamp, right? So, I mean, if you see here, I have task. So in each bucket, they are ordered by the timestamp.
Yeah.
So that's how they are laid out. And now what we want to do is we want each worker to pick the task with the smallest timestamp, which has not been actively processed or has not been already processed, right?
In
And
this case, just to clarify, you're using the timestamp itself as a proxy for the task ID because
yeah.
you've made it, yeah, right.
Mhm.
But anything else that is sort of a representative and unique could also be used. Some sequence, monotonically increasing sequence could be used also. But I see that you have used create timestamp both as a unique ID for the task and as a way to kind of get your FIFO order.
Yep, yep.
Okay.
Yeah, I mean, ideally you would have some other ID to avoid duplicates. Yeah.
Yeah, that's fine.
And yeah, we insert some tasks. I mean, this is just trying to insert tasks, like 100,000 tasks from now till some point back in time. I'll skip this. But the key thing here is we have a view again, right? But now we pick uh, from the buckets. So we try to search tasks in buckets, right? And then here we still have a limit one for update skip log. So what happens is each worker is going to read a row from all four buckets, find the smallest one, and then try to log that, right? And if it's not able to, it'll try to find one from each bucket again, and then try to log that. So yeah.
And I think it's just what I wanted to just clarify one other. If you could go to the previous slide,
Mm-hmm.
um, and yeah, maybe even one slide before.
Yeah.
See, the order of the primary key is important. So we're using, in this case, we're using the bucket to hash partition across a bunch of shards, but within each shard, it is sorted. So they are n sorted streams, and that's why the FIFO order may not be perfect. Sometimes you may get if you go to a different bucket, you may not be exactly getting the FIFO order, but they are n sorted streams, and that allows you to efficiently pick a next valid candidate. So yeah, let's keep going.
Mm-hmm. Yeah, and let's try this out as well. So actually, if I quickly see this, I mean, yeah, it's the same procedure, right? We just have this view now, and let's try this out. Um, so if you see the throughput is not as good as fan out because obviously we want FIFO ordering here, so there's some overhead there. We are trying to sort of pick from these n streams. Yeah. So one thing, if you notice, the throughput slightly drops, right, over time, and the latency increases um, over time. Now, the reason for that is, let me, yeah. So we have this tombstone problem now. So the workers keep picking tasks from these buckets, and you keep deleting them, right? So you have these delete markers as well. Now, if the worker sort of does a scan, it has to go over these delete markers and then find the next sort of task which is not yet deleted, right? I mean, this is also because we are an MVCC database, so we keep the deleted markers as well, those versions. Uh,
And this is true of other databases too, because of multi-version concurrency control. Older rows aren't immediately reclaimed, and this is what enables features like readers not having to take locks, point in time restore from backups, being able to move to an older version of the database. So there are advantages you get, but this is a practical issue that happens in most databases. But yeah, let's cover what are some of the mitigations for this.
Yeah. So one thing you could do is, when you scan, you keep track of what rows you have already skipped. So sort of like a last seen timestamp of the task that you executed, so that you can directly jump to that place in the bucket and start scanning from there, right? So you don't have to go over all the delete markers again. If we assume that you sort of keep track of, oops, yeah, the last seen timestamp, you can just start scanning from that point, right?
Yeah,
And
and the yeah, why don't you illustrate that, and we'll talk about a little some care that has to be exercised in figuring out the last seen timestamp.
yeah, so I have this. So the only difference now would be that, in the DQ function, I'm taking a last seen timestamp, so that we can start scanning from that point. And let's actually, so I won't be using YSQL bench now. I have a Python script, because we want to keep track of the last scene, in our process, right? So the throughput here does not drop, right? If you sort of keep track of the last scene. Yeah. And
Exactly.
I mean, one thing we could actually, let me also show you the explain plan, I don't know if that would be useful, but if I go back to the queue without the tombstone, I mean, the last scene tracking, right? And let's say we dequeue some tasks, right? Let it run for a few seconds, and we'll try to do an explain plan on the select for update itself, to see if, I mean, how would you detect that you're sort of scanning tombstones, right?
Yeah.
Yeah. So yeah, we have some tasks dequeued, and so what I'll do is, if I actually, uh, let's okay, we have this dequeue function, right? So this was the select, which was scanning and picking a task.
Correct.
Uh, we have this nice utility. So in Postgres, you have explain analyze. We have a few more options like debug and dist. I think this stands for distributed. So if you run this against a statement, oh, let me remove these because it is
Yeah.
not a procedure, right? Yeah, you get all of this information as to how many rows you scanned on DocDB, right? On a storage layer, how many rows you skipped or seeked, etc., etc. How many next did you do? So there's this field which is obsolete keys found, and this is basically the number of tombstones that you had to skip over, right? And it's 782 and so on, right? These are the different sort of buckets, right? Yeah, I mean, and this number will keep on increasing if I keep running.
Until a compaction runs or until the
Yeah.
MVCC versions are cleaned up. But
Yeah.
that's where I guess once you start passing the hint to say, hey, I've already seen up to this job ID or this timestamp, we seek to the correct location rather than searching from very old timestamps. Yeah.
Yep. Yeah. And
There are a few questions from the audience, but I wanted to wait till you get to this.
okay.
Yeah. So, anything else before you go to the summarizing slide? If you could stay on the previous few slides.
Previous view. Yeah.
Um,
Yeah. I think. Yeah. This was all, I guess, roughly.
So one thing I wanted to point out in tracking the last seen timestamp,
Mhm.
it is better to be correct and conservative than aggressive. And what I mean by that is, let's say workers B started working on task 12 and
Mhm.
worker C started working on task 16, right? And worker C completed task 16. It is not safe for them to say that the last in timestamp is 16 because 12 might still be being worked on, right? It is not necessary that these people complete their work.
Yeah.
So if uh, so it is better to track the minimum across all workers and start the search from a more conservative number saying, hey, I know up to 11 is guaranteed completed, but I don't know about 12 yet, or because it might still be being worked on, right? So somehow all these workers have to agree on what is sort of a minimum safe value to pass back to this pagination state. Otherwise, you can get it wrong. So I think that's one detail that's I thought it was worth mentioning.
Yeah. That's right.
In your test program, are you handling that case, or how do
No,
you?
I'm not handling that case in the
Okay, yeah.
test here. Yeah.
The second, okay, now let's go to some of the questions. Like there's a question like, hey, can this replace the need for solutions like RabbitMQ? And I suppose it extends to things like Kafka and so on. So
Mhm.
um, I think the general answer is like some of those messaging services uh, are very very verticals focused on messaging, and they've done a lot of like their storage layout, all of that is super optimized for the messaging use case, right? Whereas there may not be as much a focus on things like, can I do point in time recovery of my database, and they don't have to support random reads and random writes. So yeah, there might be valid use cases to pick a data infrastructure which is specifically optimized for messaging. But for many, many workloads, you have to weigh the complexity of bringing in two different data infrastructure components, developing expertise on it, figuring out how to make them disaster proof, active, resilient. So for many workloads, it might be an overkill to bring a messaging specific, infrastructure. Databases are very general purpose, and if some attention is paid to some of these, things that Piyush has covered in this talk, databases themselves like YugabyteDB can be a very good alternative, and they can indeed, replace some of the workloads that otherwise would need to go on something like RabbitMQ or Kafka. Um, this another question. It's like, um, is hot start still an issue if you're using a single UUID as the primary key, right? So let's go back to your create table statement, uh, and yeah.
Yeah.
And there are two cases like, if you're using a single UUID as the primary key, like this first example, then you're giving up on ordering guarantees, right? But then it is not an issue if you use like the strategy that Piyush had in the next slide, on how you start the search rather than always starting the search from the head of the table. If you use the union all technique, if you could show that, yeah, you can basically avoid the hot shot issue with this approach that you're seeing, to start the search at a random UUID. But if ordering is important, then then you pick a primary key in Piyush's second approach, where either the task ID, which is some monotonically increasing number itself, is your primary key, but then it will become a hot shard. If you have a natural set of partitions, then like tenants or something, then that is a way to avoid the hot shard issue, where instead of the bucket being first portion of the primary key, it will be like your tenant ID or something. But if you don't have a natural tenant ID, then bucketizing it this way, so that you're spreading the queue. You're kind of like pretending there are four queues here rather than one queue with a hotspot. There are like four queues with four hotspots, but that is a good technique to redistribute the load. And you can use a mix. You can, if this table is also needs to be randomly looked up by the job ID. One thing you could do is your main table could be organized by the job ID as the primary key, and the primary key he's showing here could actually be an index view. So you could create a separate index with the right number of buckets, and ordered by the timestamp, right? So that way you can both look up a job ID directly, but also a worker could find the next job to work on, right? So you can use a table with a primary key and an index to look at this data in two different dimensions. Yeah, you can, you go, over to you, like, for.
Yeah, I mean, so uh, this was about job queues, right? Use skip logged to avoid waiting for others while they are executing tasks, and try to fan out the search, and even when we are inserting stuff to a table, if it's hitting the same shard, that's a problem, right? A hot shard issue. Spreading the load, uh, uh, can be achieved with sort of sharding, and we sort of saw FIFO queues right now. It's like having these n streams and then picking the smallest out of these. The syntax was too concise, right? I mean, that's the power of PG as well. So if you, yeah, see this, right? Pretty concise, but under the hood, I mean, there's a lot happening, right? We sort of do this like end streams thing, and there's consistency locking, etc. So that's the benefit here. Plus, yeah, we need to be mindful of the tombstones, right? Because this is multi-version concurrency control. Yeah, and I don't know how we are doing on time.
We are a little over time, but what did you have in mind?
Uh, yeah, I mean, join our community Slack if you have questions around this. I know this was a pretty quick talk. There were a lot of cases, right? But join the community Slack, yeah, and I'll be happy to answer questions there.
And
Yep.
in fact, coincidentally, yesterday there was a very interesting thread on the community Slack
Mm-hmm.
where a user was trying to compare implementing a job queue using our Cassandra compatible interface YCQL versus YSQL. And yeah, it's an interesting discussion. I definitely agree with your observation, like with the syntax of, like, with the support for views, the union all kind of approach, the general observability, the enhancements that have gone into explain, analyze, to look at a lot of the raw metrics on the SQL side. Yeah, the building blocks generally are very powerful on the SQL side, and yeah, but both approaches work. But in general, like for newer use cases, I would say using YSQL, the SQL interface as the building block, is the right way to go.
Okay.
In fact, I think the user is online today, and the user was interacting with us on the community Slack. So
Mm.
yeah, good to have you. Great.
Yeah. Thanks. Thanks
Uh,
everyone for attending. Yeah.
yeah, thank you everyone for joining us on another episode of YFTT, for engineers by engineers. And I think we are somewhere around the 150th episode of this series, if I'm not mistaken. Yeah, I think the title says episode 150. So really feel good about all the content that's available on YouTube playlists and so on. And thanks again to everyone that joined and asked questions. Over to you, Piyush, for closing comments.
Yeah, thanks for joining. Yeah, it's a really, powerful way to create a job queue, I guess, using Postgres sort of syntax. Yeah, yeah,
Right. Have a good rest of the day and weekend, everyone.
yeah.
Thank you.